Okay, so we've done coupled differential equations by Euler's method. Now we're going to talk about, and we'll get to this at the end, but this is called a phase diagram. Phase portraits for a system of two proposed initial conditions. The thing starts here at the middle and then spirals out with slightly different spirals depending on the initial condition. It's slightly crazy, huh? We'll see if you can learn how to do this year. Um, yeah, there's a few things, and this is one of them that we're not going to spend 3 weeks trying to learn.
Because
We
we've
don't,
seen on the test work.
well, you could learn it in 3 weeks, but you're going to sacrifice four other questions to get part B of one question. That makes sense? It's one of those, because of the limited time, I'm going to give you a little introduction. You'll see if you can get something, or a point out of three or something like that. And that might be what you get. And if you take Calculus 4, you'll actually get 3 weeks, maybe. You'll get a couple of weeks to do it. Apparently, a lot of times it's at the end, though, and nobody gets to it. If you take differential equations too,
I don't have to, right?
they just start calling them differential equations. I've been calling it Calc 4 so you have a reference point for where does it normally show up. Um, Throughout this subtopic, you'll think about the relationships between variables and how they can be modeled. The previous dis the subtopic discussed the predecessor-prey relationship. Oh, we didn't do that. Let me show you that. We're just going to see this. So, remember how we made at the end kind of the diagram with all the dots with the sequences? Come on, load. This is going to be one for a predator-prey relationship. So this is what the constants mean, and these are my coupled differential equations. dw dt is the rate of wolf population over time versus the rate of deer population. Okay? So we can see that a constant times wolf population times deer populations minus another constant for death rate of wolves times wolf population gives you the change in wolf population. Okay? The change in deer population is the constant growth rate, or that'd be like birth rate for deer, minus the constant of proportionality between both deer interaction. Wolves limit deer population, right? If there's not enough deer to eat, that limits wolf population. You guys have all heard this in biology, I'm sure, right? And if we put it, notice what we get. This is not a relationship over time. The relationship over time would probably go up and down, and you could graph each of these over time. Does that make sense? What we have here is a relationship of wolves to deer, and I don't know which way it goes, but it basically makes this circle, right? Okay? It makes a circle. It's a cycle. As the wolf population goes up, the deer population goes down. As the deer population goes down, the wolf population goes down. As the wolf population goes down, the deer population begins to recover and go back up, which leads to an increase in wolf population. That makes sense? So we get these kind of cycles. And what we've been working with in our cycles is an approximation method. Well, today we're going to learn a method where we can get exact solutions. some of the time. Okay? This method does not work. There's lots of differential equations that this does not work for. Okay? But the ones that it does work for, this is actually easier and quicker than Euler's method. And it gives you exact. So, the ones that it works for are in this form. A, B, C, or D can be zero. So you don't have to have an visible X and Y in each part, but you do have to have nothing can be more than first power. Okay, notice that X is not squared, it's X to the first, Y to the first.
Wait, in order for this to work, X has to be just X.
X has to be X, Y has to be Y. Okay, no Y squareds, no X squareds, no square roots, none of that. A, B, C, and D have to be constants. That means numbers, right? We don't necessarily have to know what they are. To apply it, yes, we kind of do, but okay. So it leads to this. We have, we will get a single equation, a vector, so x and y vector, with a constant a and a constant b that we'll solve for. The number e to the eigenvalue 1t times eigenvector 1 plus b e to the eigenvector 2t times eigenvector 2.
What?
I'll show you how to do this.
Okay, this is
It's not as bad as you think. I'm gonna move it up. The exam tip says this formula is in your formula booklet. Okay? Everybody got that down? So let's take a look at this. So, first thing I'm going to do, and I'll do the first one by hand. I'm going to write this into a matrix. That's essentially A, B, C, D. Does that make sense? And then I'm going to write it into the eigenvalue matrix.
wait, how are you writing this matrix? Oh,
A, B is 0, C, D. That makes sense? Just like I would if it was solving a system. So then to find the eigenvalues, I go 3 minus lambda times 2 minus lambda. Remember, it's AD minus BC equals 0. Well, this is nice. -6. Actually, I don't even need to expand this out. I've got it equal to 0. What are my two values of lambda?
3.
-3. -3 minus -3 is 0. What's 0 times -1? It's times. That worked out nicely. Okay. So now I know my two eigenvalues. How do I find my eigenvectors? That one's not going to work. So this is negative x minus 5y equals 0, correct? So 5, negative 1.
Yeah.
What did I do? I essentially swapped negative 1 and 5. I know that they've got to add up to 0, right? So if I plug in 5 for x, I need to plug in negative 1 for y. I plugged in negative 3 into this and made an equation that this doesn't work out because that's 0x and 0y. Um, so essentially I'm multiplying this times this matrix times xy equals 0, 0. And I'm plugging in negative 3 for lambda. Let's do the second one. So now let's just ignore the first line. Negative 1x plus 2 minus 2. Well, that one's not working out. Okay, I see what I can do with my eigenvectors. X in this case has to be 0 for this to work, doesn't it? And we'll just use 1 for the other one. Let me double check my other eigenvector. Yes. Wait, they got positive 1? Oh, I was dumb here. This is supposed to be positive 1. That's a plus. I don't know why I made it a minus. So I'm going to write down some of my known things here up here. Everybody understand how I found those.
I'm not gonna lie. Yeah, me
So you
too.
just to the eigenvalues into the matrix and then.
And then multiply it by xy. And that gives me these equations down here. That this works out to be, this one is fine. If this is going to be 0, x also has to be 0, correct? It has to be 0 plus 0 equals 0. So that's 0, and then pick any y you want. But 1 is the easiest. This one, -1 times x plus, this works out to be when I plug in -3, 5 plus 5y equals 0. So if I pick an x and a y, it's 5 and 1. Take this matrix, I plugged in -3, right? That makes it a 5. -1 times x plus 5 times y equals 0. That's how you get eigenvectors. That's just the rule and the definition for getting an eigenvector. That's why we reviewed that a couple weeks ago. I guess we'll review it again on the next one instead of using your calculator. Okay, now I'm going to use my form. The x factor equals A, E, eigenvalue 1 was -3. There's a t in this up here, right? Times the eigenvector. And plus b e to the 2t times this eigenvector. So if I multiply this out into vector format, I take this thing multiplied by the 5 plus this multiplied by the 0 for the first line. Does that make sense what I did? The second part here would be plus 0, because 0 times this just makes it 0. So I took this times 5 plus this times 0. And that's the top line. Then I took this times 1 plus this times 1, and that's the bottom line. And that should equal,
Is the bottom fine, or is that just an extra little?
that's just an extra little, no, there's no derivatives in this right now. So this is going to essentially equal x, y at, so it tells me these initial conditions, x0 and y0. What does that mean about t? T is 1. Yeah, t is 0. Sorry. It asks me to evaluate it at t is 1 later. So 1, 2 goes with 5a e to the -3 times 0 plus a e to the -3 times 0 plus b to the 2 times e to the 2 times 0 What's e to the 0? 1. Anything to the 0 is 1. So this whole thing becomes a 1. So I get 5a equals 1. And 2 equals a plus b. Good so far. So a equals 1/5. Now I can plug that in for the 2 equals a plus b and get b equals 9/5. And I get the equation then. 5 times 1/5 is just 1.
Oh, yeah, because five about.
Because it's 5a, right? Oh, wait, no. Should be 1/5 if I'm writing it there. Plus b is 9/5 e to the 2t. Now I'm plugging in 1. And I'm going to write it in both forms because it wants x and y. Now 5 times 1/5 is just e to the negative 3t.
Was there a point in going back to the other formula or the other like way of looking at it?
With it
Just,
written out,
yeah.
they'll probably want to see it on the test. So now I'm going to plug in 1. Yeah, I could just plug in directly to,
And will they normally tell us if they want it in that form or?
yes. Half just wanted to write it out for you to see it. But yes, you could plug directly into this for the solving purposes. And you're going to have to stick that into a calculator because I have no idea what e to the negative 3 is. Okay. But for the purposes of time here, we're just going to scroll down and that's what it works out to be. This is my final answer in vector format.
This was supposed to be easier than the
Euler's method?
more proximate.
So let's talk about what Euler's method asks us to do here next.
About one.
Compute the approximation numerically using t equals 0.0002. That means I need 500 steps. That's even going to be a pain on the calculator. Okay. Because you'd have to scroll down to 500. And yes, they just kind of jump through them, don't they? Until you get to x, y. And there you can see that they are pretty close. Euler's method going by 0.002 gave me a pretty good approximation. Could I do this a lot faster on a spreadsheet? Yeah, because I could scroll faster than the calculator. Okay, you could do this in Google Sheets. That makes sense? I want you to practice it when you're doing them on the calculator because that's what you get for the exam. That makes sense? We ready for example 2? Okay. I guess I better go. So what's my matrix? In an eigenvalue finding form, it's this. So again, I did AD minus BC equals 0. This time I'm going to have to expand it out. It's 10. A metal factor. Oh, lovely. This is good. Okay, so that makes sense. Lambda 1 equals -2. Lambda 2 equals -5. Now let's do our eigenvectors. Let's plug in. 4 minus -4 minus -2 is -2. -3 minus -2 is -1. I don't really need both rows because they both give me the same eigenvector, correct? So x is 1, y is 2. Just gonna switch those values. For my second one, 4 minus -5 is 1. -3 minus -5 is 2. And I end up with x plus y equals 0. So they're just opposites, correct?
Yeah.
My general equation then, ae to the -2t 1, 2 plus b e to the -5t 1, -1. Sorry, I'm gonna have to cram this in get just a hair tighter. Okay. Now we know the initial conditions, the zeros. So that leaves us with 1 equals a plus b. negative b e to the negative 5 times 0. So I multiplied them out and plugged in my zeros. Can I solve this system? And what's the easiest way? The easiest way to solve this system. Add them together, the b's cancel, don't they? 3 equals 3a. So a equals 3. That means b equals 0. Oh, yeah, a equals 1, sorry. 3a equals 3a equals 1. So my equation simplifies down a bunch since b equals 0. X vector becomes e to the a is just 1. I'm interested in t equals 2. I'm interested in these x and y's. 1 times e to the negative 4 is the first one. 2 times e to the negative 4 is the second one. And you can get decimals for those, correct? It now wants us to compare it to using Euler's method. It's negative 2 times t equals 2 is what it wants me to evaluate at. Again, it's making us do 500 steps of Euler's method. That would be awful if you had to do that by hand. It's bad enough on the calculator because it doesn't scroll down super fast. So let's see what we get. So they get that when you approximate, and you get this with using the exacts.
So much.
Yes, I'll keep the recording going. This kind of makes sense.
Yeah.
And like the next one, we're going to find the eigenvalues and eigenvectors on your calculator. You just can't do that on the exam. But as you're doing, hopefully that's enough review that you can just like, oh yeah, I know how to do that. And we can cut out a little bit of time as you're learning the new thing. Okay? So now we've got this. It says find the general solution. Well, what's my matrix? 4. Let's go ahead and find our eigenvalues and eigenvectors on the calculator. I didn't find a good spot to put that. Seemed like a good spot at the time. And I am going to store this in A. Everybody remembers how to do that? So now menu, matrix and vector, advanced. Eigenvalues of A, 5 and 1. And we'll do eigenvectors.
Over one. And one over two.
1 over 1 and negative 1 over 3, I believe. That's definitely 3 times as much. Okay, so we'll go back to the other screen. I have a feeling they're going to go 3 over negative 1, but let's see. Oh, yep. We'll just do the same one that they did to make our life easier when comparing. Or they did 1 over negative 3. So they swapped where the negative sign is. It's like this book tends to put the negatives on the bottom. So now A e to the 5t 1 plus b e to the t 1t, so just t 1 negative 3. So now when I plug in, we've noticed that the e to the t's when it's 0 is always just 1, right? So 1 times a plus 1 times b. A plus b equals 0. Okay. A minus 3b equals 1. I'm going to multiply the top equation by negative 1 and add them together. If b equals negative 1/4, a has to equal positive 1/4, correct? So now it asks me to do t equals 0.5. I'm not going to put it back into that original form because it doesn't ask me to. Oh, a is 1/4. E to the 5 times 0.5. B is negative 1/4. I don't know why I keep writing 0.2. So I did -3 times the -1/4, so -3b here. That's where I got the 3/4. And then I stick that into a calculator. Or look down here, and I get those. The approximation again went to 500. And I get 2.634.28, 2.614.26, off by 2/100ths. You get pretty good approximations with Euler's method. And it's the best method we have sometimes. Does that kind of make sense? Like you're gonna have to practice it, but it's just using the formulas. This is where it's going to get a little bit rough in the qualitative techniques. So this is going to be describing, it's basically making the diagrams. So I showed you the spiral one. This is how to make them. Okay, and it's called a phase portrait or a phase diagram. And the eigenvectors become very important. The eigenvectors essentially become slopes. Do you guys understand how -2, 1 looks like this? Means down 2 over, no, over -2 up 1.
Yeah.
That makes sense? And 1, 1 is 1, 1. The vectors are essentially slopes. So, important piece of a phase diagram is putting the eigenvectors down. Okay? These will always kind of either go out, like they're asymptoted along one of these eigenvectors, or they will go to 0. Okay? It's different if the eigenvectors are non-real. Do you guys remember having a non-real eigenvector way back last year? Some of them will have an I in them. Or if the eigenvalues are imaginary numbers, which is valid. So, the key thing here, which is the larger of the two eigenvalues? Values,
Oh,
4. And that corresponds with 1, 1, which means, let's say I start here. This is eventually going to trace to follow that eigenvalue. If I start down here, it's going to trace and follow along an asymptote along that eigenvalue or eigenvector that corresponds to the larger eigenvalue.
And it's true for all points, no matter how close to the 1, 1 line.
So if I pick a point to start from here, any point in this field, if I follow it and I follow these slopes, I think I made it go a little bit too quickly, but it'll eventually trend towards this eigenvalue like it's an asymptote or eigenvector. But it always has to be the larger one unless it is, if it is on this eigenvector, it's going to stay along it. But if it's not on the eigenvector, even this is going to end up hooking, like, let's do one here in red. Even this one is going to end up hooking eventually to be along this eigenvector. That makes sense. And what you're going to have to show with these diagrams, if you can put the eigenvectors on, you get a point. If you can make it show that it's going to it, you just have to, it's always the eigenvector that corresponds to the larger eigenvalue. Unless, of course, it's on the other eigenvector.
How do you know which eigenvector it'll go to? The larger eigen.
The larger eigenvalue. So we've got the two eigenvectors, right? And which one is my asymptote that it's going towards? The one that has the larger eigenvalue. So 4 being larger. Positive numbers are always greater than negatives. Okay. And that's like as t gets large, if you've got e to the negative t, that's going to 0, right? That's why the larger one dominates. I would write in words asymptotes to the eigenvector corresponding to the larger eigenvalue.
Diagram, news, or the eigen.
It's, yeah. So I'll show you an example here, okay? And then I'll show you where, remember the method we used last Thursday with the sequences? That sequence thing that with your calculator will trace out essentially the phase diagram in dots. So here we've got this. Okay, sketch a proposed trajectory. I think we already did this one. We had these eigenvalues and these eigenvectors. Okay. 5, 1 is that, correct? 0, 1 means it goes 0 on the x, that's a vertical line. Anytime x is 0, it's vertical. Anytime y in an eigenvector is 0, it's horizontal. The larger eigenvalue is here, so it asked me starting value. 1, 2. So that's where I'm starting from. That's my point. Okay? It isn't on the blue eigenvector, so it's going to trend towards this eigenvalue, or this, yeah, the orange eigenvector. Okay? Putting this into let's put this into the calculator to remember how to do this with the sequences. So I'm going to write this off to the side. And remember that xn plus 1 equals xn plus, we'll just do 0.1 because I don't want a million of these, to the xn prime, right? Do you guys remember this from Euler's method? 0.1 being step size for this.
Just chose it.
I just chose my step size. I didn't want to go smaller than that. But I want to save the document now. going to add a graph. And I'm going to do these. I have to add a sequence. UN plus 1 fits my form. Xn is U1 of n plus 0.1 times my x prime is -3 times, so it's -3x, right? X is U1n. Initial term was, the x was 1. I'm just going to go 0 to 40. Now I'll do U2. N plus 1. U2 n plus 0.1 times, this one is -x, which is U1n, plus 2, y is U2n. Okay. The initial y was 2. And I don't really want these displaying, so I'm going to go tab up and uncheck them. Because it's going to be harder to see what is happening. Now I'm going to go graph entry edit sequence again. And this is what it's custom. U1n is my x. U2n is my y, and I still want it to be 0 to 40. See how it's going there? I wasn't asked to approximate it, I'm asked to make a sketch. And it just gave me essentially my sketch. Connect the dots. Okay. That kind of makes sense, the connection to the phase diagram. So the phase diagram, so you see the dots. See the phase diagram? The dots are just tracing out steps along it. So that's why that method, which I think is harder for getting your numbers, can be very useful, though, to understand and be able to do. Okay. Now let's look at this one. So it's starting at 4, 2. So here's my eigenvalues and eigenvectors. Which one of the two is larger? The second one, the -2, right? So the fact that it's negative tells me it's probably going into 0. So if your eigenvector is positive, it's going away. Because keep in mind that you had this for a formula, correct? Times these guys. So if lambda's negative, e to the negative something is going to 0. Does that make sense? E to the positive something is going to infinity. So if your larger eigenvector is still 0, it's going in. It starts at 4, 2. What you need to show on a test is that its starting point, you got to show the arrow which way it's going and that it's coming along the eigenvector to 0. That makes sense? If it was on this one, it's got a negative eigenvalue, so it would go into zero as well. If it were positive, well, that would make the whole thing go away, but does that make sense for that one? I should have some time after the calculus lesson tomorrow to answer questions on these. Okay, looking at this one. New coupled system. Which eigenvector am I following? 1, 1. And I'm starting at 0, 1. And it's got to go out because those are positives. Given enough time, this will eventually hook in a little closer to this eigenvector, but that makes sense. Something they might look for is that you started with the proper slope. How do you get the proper slope? dy dt over dx dt. Okay. Plug them in, looking at my original thing. Here's my point. 1. 1 is, oh wait, 1 is the bottom. dy dt is 2. So start with a slope of 2 when I plug that into those. That makes sense? So I'm plugging in 0. 4 times 0 plus 1. So dx dt is 1. dy dt equals 2. So my slope, where I start, is 2. I know this is a lot. This one, initial conditions, so 0.75. You get complex eigenvalues. Okay? Which means it's curving. Which means it's a spiral. Complex eigenvalues mean spiral. This number right here is positive, which means it's spiraling out. If the real part of the complex eigenvalue is positive, it spirals out. If it's negative, it spirals in. More detail in that is left for later classes. Like this one is negative. It starts out here, it's going to spiral in. Again, if you show it spiraling in and ending at 0, 0, start at the right point with approximately the right slope. Check. Full points. Okay. This last one, we get just plus or minus I, means it's going to spiral in a circle. Or an ellipse, I guess. You can find the slopes as it goes through the axes.